So let's move on to 21. Item 21 says we were supposed to look at the data in this table here, and we have a gas, we have nitrogen gas, and the equilibrium partial pressure is A for that. We have hydrogen gas, and the equilibrium partial pressure is B for that. And then we have ammonia, and the equilibrium partial pressure is denoted by C, okay? So they're asking, what is the expression for Kp for the equilibrium of nitrogen gas plus 3 moles of hydrogen gas being in equilibrium with 2 moles of ammonia gas, right? So remember now, Kp is just going to be equal to the partial pressure of the product species, which is ammonia, raised to its stoichiometric coefficient. So it's going to be the partial pressure of ammonia squared divided by the partial pressure of nitrogen raised to its stoichiometric coefficient, which is 1. So that's partial pressure of N2 raised to 1 times the partial pressure of hydrogen raised to 3. So that's what we have here. And so in the table, they told us what the equilibrium partial pressures are. And because this is an equilibrium constant, we need to put the equilibrium partial pressures here, right? And so for ammonia, they said it was C. So we're going to put C here, and we end up with C squared in the top. And then nitrogen, they said it was A. So we're going to put A raised to 1, which is basically just A. And then for hydrogen now, we're going to put B, and we're going to raise that to 3. So we end up with the Kp expression being C squared over AB cubed. And that is, what's that? C squared over AB cubed, that's D, okay? So the answer for 21 here is D. All right. So moving along to 22 now. 22 says, which of the following are Bronsted-Lowry acids? So a Bronsted-Lowry acid is a proton donor, right? That's the definition. So it should be a compound that has a hydrogen or a proton that it can donate, right? And so if we look at this, we see that this is what the ammonium ion. And if the ammonium ion donates a proton, we're going to end up with ammonia, and that's possible. So this is a possibility, right? We look at this phenol here. There's a hydrogen here that's capable of being removed, thereby being a proton donor. And so this could be a Bronsted-Lowry acid, right? And then here we see that we have the kind of like an ethanoate ion, right? So there's no hydrogen here. The hydrogen was already removed, and so there's nothing else to donate, right? There are no protons to donate in this molecule, and so this one is not a Bronsted-Lowry acid. And so our final answer then will be 1 and 2 are Bronsted-Lowry acids, because there are proton donors in these. They can be proton donors, and so the answer for 22 is A. Okay? All right, so moving along to 23 now. 23 says, what is the Kw value, right? What's the Kw value of 2 mole per dm cube sodium hydroxide aqueous at 298 Kelvin? So what's the Kw? What's the Kw? That's the ionization product of water, right? So that's Kw is equal to H plus times the concentration of H plus times the concentration of the hydroxide ion. And that's a very fixed number. That's a number that can't really change. It's just fixed. It's a constant, right? And so that constant is actually 1 times 10 to the negative 4 mole squared dm to the minus 6. And that's what the number is. That's what it always will be. And so it doesn't matter what the concentration of the solution is or the base that's being contributed. The Kw value will always be 1 times 10 to the negative 14. And so that's why C is our answer here, okay? It's a constant. It's a number that you just have to remember that that's what it will always be, okay? That's the ionic product of water. It's always going to be 1 times 10 to the negative 14. So that's that, okay? 23 is C. So moving along to 24 now. 24 says, which of the following indicators would be suitable for use in titrating a strong acid against a weak base, right? So they're showing us some indicators here and their pH range. So the key thing to remember here is that when we're doing these titrations, the indicator that will be most suitable is one that changes within the pH range where your endpoint will be, right? So for example, so I'm titrating a strong acid that has a pH of, say, what, between 1 and 2. That's a very strong acid. That's where the pH would be. And I'm titrating it against a weak base, right? So I'm adding a base to that, and the base, the weak base, is gonna have a pH between 8 and 9, right? So I'm gonna start with my strong acid in my beaker, and as I'm adding the weak base, right, the pH is gonna be raising from 1 up to this region here, right? So I want to choose an indicator that changes within that range, say anywhere from 2 to 8 would be good, right? Anywhere within that range, if I have a pH indicator that changes in the middle of this range, it would be good for me. So I'm gonna look down here at my indicators. I see bromophenol blue. It changes within the range 2.8 and 4.6. That might work, right? It fits nicely in here, so that might work. Methyl red changes in this range, 4.2 to 6.3. So it would fit nicely in the middle here, and I'll be able to see my endpoint. So this is good, right? So that might work for us. Alizarin yellow changes at a much higher pH range, from 10.1 to 13.8. We're not going to quite get there, right? Because it's a strong acid being titrated with a weak base. We're not going to be all the way up here. That's too high. And so if I were to use alizarin yellow, I would miss my endpoint. So it's not suitable, right? So that's not suitable for this titration of a strong acid versus a weak base. Okay? So my answer for 24 then would be 1 and 2 only. And so that's B, okay? So 24 is B. So moving along to 25. 25 says that a buffer solution consists of ethanoic acid and sodium ethanoate solution. So that's CH3, COOH, that's my acid. And then this is gonna be my salt of that acid. So it's gonna be CH3, COO minus, and that's Na plus, right? Sodium ethanoate. So that's what my buffer system consists of. So which equations show how the buffer maintains a constant pH in solution? So remember, the way that the buffer works is that it maintains a constant pH by resisting any change that you impose upon it, right? So if you add H plus ions, it's gonna shift a particular way. And if you had a base, it's gonna shift in a particular way, right? So this one right away, this has nothing to do with what we're doing here, because where is this ammonia coming from and what is this, right? So we can rule out one. One has nothing to do with what we're doing. So that's just one to throw us off. So let's just get rid of it right away. That's not gonna be how the buffer maintains the pH or how it buffers, right? Now let's look at 2. If we have this, our sodium ethanoate, so we have this ion here, and we add in H plus to the system, then yeah, it's gonna combine with this ion to form acid, and that would be a way to maintain the constant pH. So this is correct. Now, if we add in base, then the base would be what? Base is our proton acceptor, so it can take off the proton that's coming from the acid portion. And then we're going to get CH3COO minus and water being formed as well. And that's one way that this particular buffer system can maintain pH. And so 3 is also correct. And so 2 and 3 only are our answers for 25. And so that's C, okay? So our answer for 25 is C. And we are moving along to 26 now. 26 refers to the following reaction. So here we see that we have ethanoic acid in equilibrium with H plus ions and ethanoate ion here, okay? So they're telling us that the concentration of sodium ethanoate, so this one here, right, would be 0.5, and this species here, which is our ethanoic acid, would be 0.3 mole per dm cube. That's the concentration of it. And then now they're saying, given that the Ka of the ethanoic acid is 1.8 times 10 to the negative 5, because it is a weak acid, what is the pH of the buffer solution, right? Buffer solution. Whenever we're trying to find the pH of a buffer solution, guys, just remember we're always going to use the Henderson-Hasselbalch equation. That's the easiest thing to use. And that just says that pH is equal to pKa plus the log to the base 10 of the concentration of your salt, which in this case would be your sodium ethanoate, over the concentration of your acid, which would be 0.3 mole per dm cube, right? So we're just gonna plug in the answers, the values that we have, right? So pH now is gonna be equal to the negative log to the base 10 of this 1.8 times 10 to the negative 5, because that's our Ka, and how we find pKa is a negative log of this Ka, so that's here, plus log to the base 10 of the salt concentration, which is 0.5 mole per dm cube, and the acid concentration, which is 0.3 mole per dm cube, right? So when we do that now, what we're gonna get is that we're gonna get that this first part, the pKa, is 4.74, and then we're gonna get this final part being 0.22. So when we add those two together, we come out with a pH of 4.96. So this is our closest answer there. So B is the answer here, okay? So B is our answer for 26. Remember, all we're doing is we're applying the Anderson-Hasselbalch equation. That's what we use to find the pH of buffer solutions, okay? All right. So moving down to 27 now. 27 says, when solid silver chloride is added to a solution of potassium iodide, a yellow precipitate of silver iodide forms because, why do we get a yellow precipitate of silver iodide, right? So, is it because the chlorine is more electronegative than iodine? That's not why. That has nothing, electronegativity doesn't really have anything to do with precipitation per se, right? So this one is not correct. That's not the reason why we have a precipitate forming, right? Potassium chloride and potassium iodide are both soluble. Well, yeah, they're soluble, but that has nothing to do with why we see a precipitate in the case of the silver iodide, right? Is it true that silver chloride has a lower KSP than silver iodide? That's not true. So the lower the KSP is, the higher the probability of us forming precipitates, right? So the silver iodide is actually what has a lower KSP value than silver chloride. So that's why we're gonna end up getting the precipitate that we see, okay? So silver iodide, this one here, has a lower KSP than this. And so we end up seeing this as a yellow precipitate when these two come together, okay? Silver iodide has a lower KSP value than silver chloride. Remember now, the KSP is just ends up being just the, it's a measure of solubility. And so it would be the concentration of the silver ion times the concentration of the iodide ion, right? And it turns out that this number that we get in this case is less than what we would get in the case of a chlorine silver chloride solution. And so that's why we see a precipitate, right? So precipitate formation has to do with the KSP value, and the lower your KSP is, the higher the probability of you forming a precipitate, okay? And so that's what happens in this case, and that is 27 is then D, okay? All right, so moving along now to 28. 28 says, which of the following is not a standard condition for measurement of electrode potential? So now we're shifting to that section where we're doing redox equilibria, right? So which of the following is not a standard condition? So let's see what's true. Let's see what is true. Is it true that the solutions have to have a concentration of 1 mole per dm cube? That's true. Do the gases have to have a pressure of 1 atmosphere? That's true. Does the temperature have to be 25 degrees Celsius? Yeah, that's true. Metal alloys are used as electrodes? No, we don't need to use alloys. That's not true. That's not a condition, right? We just use the pure metals, right? That's what we would use. If that's what we're measuring, if we're measuring it for like a pure metal, then we would a combination of metal ions, and we would be using just the metal itself. We wouldn't be using alloys. So this is not true. This is not correct. We're never going to be using metal alloys as our electrodes, okay? So this is not true, and so 28 is D. So moving along to 29 now. 29 says, which pair of half cell potentials would produce a cell potential of 1.1 volt when combined to form a cell, right? So the way that we have to approach this one is we have to know how to calculate a cell potential, right? So we have to be able to look at these half equations and say when we combine them, would we get the cell potential? And the easiest way to do that is to say that the cell potential is gonna be equal to the electrode potential of the more positive half cell minus the electrode potential of the negative half cell, the more negative one. So let's look at A. So in the case of A, where we have this copper 2 plus and the Cu metal ion here, the electrode potential, standard electrode potential of that cell is 0.34 volts. And then in this case, the iron 3 plus the iron 2 plus is 0.77 volts. So in this case, this would be our positive one, our positive half cell, and this would be our negative one. And so if we do positive minus negative, what are we gonna get? We're gonna get 0.77 minus 0.34, and that's not 1.1. We know that right away, so we don't even have to go any further. Let's look at B. If we have our positive one is gonna be 0.34 because that's more positive, and our negative one is gonna be this one where it's zinc, right? So in this case, our positive one is 0.34. So we're gonna do 0.34, and we're gonna minus our negative one from it, and the negative one is this one. So we're gonna minus 0.76. And in this case now, we will get 1.1. So our answer for 29 then is B. And you can go through the exercise of doing these ones and convincing yourself that you're not gonna get 1.1. But we know right away that B will give us 1.1. So this is a reaction that will then be feasible, right? Because it's positive and it's 1.1, right? So remember now, we're gonna calculate the cell potential, the standard cell potential, by subtracting the negative, the cell potential of the half cell potential of the more negative one from the positive one. And in this case, our more negative one is minus 0.76. So we're going to subtract that from our more positive one, which is 0.34. And when we do that, we're going to get, so this is for A and this is for B. We're going to get 1.1 in this particular case. Our answer is B. Okay. So let's go down to 30 now. 30 says that the standard electrode potentials for dichromate and iodide are shown here. So we have this reaction here where we're going from chromate 6 to chromate 3, right? So that is as shown as it's written here is a reduction up here. And then we're going from I20 to I minus, as it's written here. This is written as a reduction as well. That's how they're normally written, right? So that's what this one is showing. Okay. From this, what can it be deduced? Can it be deduced that acidified dichromate ions, so these ones would oxidize iodide ions to iodine? Well, that's a mouthful, so let's think about that. Let's look at the electrode potential values, right? So we have this one being the more positive one, right? And we have this one being the more negative one, right? No, the more negative one is where oxidation is gonna take place, right? So this is where the electrons are gonna leave from. And so generally what we can do is rewrite this one in terms of oxidation, right? As a loss of electrons. And so what we would then rewrite it as we would write 2I minus is gonna go to I2 plus 2E plus 2E, and of course we are gonna have to rewrite that value, that cell potential or that electrode potential as 0.54, right? This is the more negative one. So this is the one where oxidation is going to take place, right? And so this one, of course, we're going to keep it the way it is, where we're having this one being the one where reduction takes place because it has a higher, more positive value for that standard electrode potential, okay, of this half cell. So let's look at it now. We have this acidified dichromate ions. It's going to get reduced. And because it's getting reduced, it means that it would be oxidizing this iodide ion to iodine. And so our answer is A. Okay? So you see how we did that analysis? we look at our standard electrode potentials for these half cells. So we look at this one and we look at this one. And we see which one is more negative. It's this one, this bottom one for iodine going to iodide. And so we're going to flip this one to rewrite it to show that this is where oxidation is going to take place. Remember, your more negative one is where oxidation takes place. So we rewrite this one to show oxidation taking place of our iodide ion going to iodine gas, just like in that neutral state, okay? So, uncharged state. So that means that it is, if we combine the half cell, it is in fact the dichromate ions, the acidified dichromate ions, that they themselves end up getting reduced, right? From +6 to +3. Because they got reduced, they gained electron, we know that they must have caused the iodide ion to lose electrons, thereby oxidizing the iodide ions to iodine. Okay? So our answer for 30 is A. All right, so moving along to 31 now. 31, item 31 and 32 refer to the following graphs. So we look at A, and what we see that we have period 3 elements, right? So this is about period 3. So we have period 3 elements, and they're showing A, B, C, and D. And they're asking now for the actual question. They say, answering items 31 and 32, match each item with one of the graphs. So each graph may only be used once, more than once, or not at all. So which one of these graphs represent the atomic radius, or how the atomic radius changes across period 3 is what they're asking. Which one of these graphs between A, B, C, and D is going to show us how the atomic radius changes across period 3. So as we go across period 3, what's happening to the atomic radius? We're adding more electrons as we go across and more protons, right? And so when we do that, we are effectively increasing the charge on the nucleus, right? And so it can better pull those outermost electrons more tightly. And as we go across, that's the trend that we have. And so we see that as we go across, the atomic radius actually decreases, right? So which graph shows that? That's C. C shows our atomic radius gradually decreasing as we go across that period 3, okay? And so the answer for 31 then will be C. The atomic radius decreases as we go across the period. So that is 31C. And so now we're moving along to 32. Which of these graphs show the first ionization energy changes across the period? So the first ionization energy is the amount of energy that it requires to take off that first electron, right? As we go across the period, does it become easier or does it become harder to take off that first electron? So we're going across the period now. What do we have? We have a higher charge, right? As we go across, we're adding electrons and we're adding protons. So we have a higher nuclear charge, but we also have a smaller atomic radius, so that pull of that outermost electron is stronger. So as we go across the period, it's going to be harder to take off an electron. And so the ionization energy is going to increase, right? For the most part, as you go across that period, your ionization energy is going to increase. So we need to find a graph that shows that, right? Of course, there are anomalies, there are outliers, right? But this C wouldn't work and D wouldn't work because those shows decrease. These two show an increase. So it would be between those two, right? And of these two, right, if we account for all of the anomalies that are there, so the ones that don't quite follow the trend, right? So let's tell you what, let's just jog your memory on what the outliers are again. So the outliers in this particular case would be what? It would be that the silicon is an outlier, right? And then we come back down to P, we drop down to P. Well, the P is an outlier. We drop down here because we're going from metals now to non-metals, right? And so we would see this particular trend here, okay? So we steadily increase, and then we see this jump for silicon, And then we come back down. So the answer here would be B for 32, okay? Well, actually, let's see. 32. First ionization energy, let's see. This trend doesn't really, I don't think this is really it. This is more of a melting point curve. So we can rule out this one. It's not B actually, it's gonna be A, right? So here we have sodium and then magnesium. So that's an increase, and then we drop down. This is an anomaly here. And then we jump up back, and then we jump down once we get over to these ones here. So the answer here would actually be A, because this show a more gradual increase with this one anomaly in the middle, right? So 32 is A, in fact, and not what I was saying earlier. So 32 is A, okay? 32 is A. And so moving along to items 33 and 34, they refer to the following oxidation states, right? So we're gonna match each element below with one of the options above. Each of them may be used more than once or not at all. So they're asking us what's the oxidation state of this phosphorus atom in here. So we know that oxygen would be -2. So everything has to add up to 0. So we'll find that P, it would be 4x minus 12 equals 0. So the oxidation state of that phosphorus has to be +3, right? So where's +3? +3 is B, so 33 is gonna be B, okay? Now we have to find the oxidation state of sodium here, right? And so this is our unknown here, that's our X here, and then this was our X here, right? And so we know oxygen is gonna be -2, and everything has to add up to 0 because it's a neutral compound. And so 2, so we have -2, and then 2 times X is gonna be equal to 0. And so that means that our value for X has to be 1, right? So A is our answer for 34. That's the oxidation number of sodium. So that is A, okay? So 33 is B, 34 is A. All right, so moving along to 35. 35 says, which of the following has a simple molecular structure? So this is an ionic molecule. Sodium oxide is ionic, right? So that's Na2O. So that's an ionic, not simple molecular. So not that one. Magnesium chloride is also ionic. So not that one. That's not a simple molecular structure, that's ionic. Aluminium chloride now is interesting because you would think it would have an ionic structure, but it's not really, because the difference between the aluminium and chlorine in terms of electronegativity is not that far. And so what we see in this case is a simple molecular structure for aluminium chloride. So aluminium chloride is actually our answer here. It has a simple molecular structure. And we know that silicon 4 oxide would have a giant molecular structure, right? That's SiO2, silicon dioxide. It has a giant molecular structure. So we know that that's not this. So our answer is C for 35. So 35 is C. And we're moving along to 36 now. 36 says, in descending group 2 of the periodic table, the first ionization energy value of the elements decrease. So as I'm going down group 2, right, the ionization energy is decreasing, right? So that's what we see there. So they're saying this is due to which 2 of the following? What causes that decrease in first ionization energy as we go down group 2? So as we go down group 2, we're going from beryllium to magnesium. We're gonna go to calcium, and then strontium, and then finally barium, right? That's how group 2 is arranged. And we're going to be decreasing the ionization energy. Now, remember earlier what I said about ionization energy is the amount of energy required to remove that first electron, that outermost electron, right? So as we go down the group now, you might remember that as we go down a group, we're adding more and more electron shell. And so that outermost electron shell ends up being very far away from the pull of the nucleus, and there is shielding of those outermost electrons as well by the intervening shells, okay? And so because of that, it's gonna be easier for you to remove that outermost electron. So you're gonna see a decrease in ionization energy. So let's see if anything here matches up with that explanation. So the atomic radius is gonna increase as you go down the group. That's true because you're adding more shells, and so that outermost electron is gonna be further away from the nucleus. So this would help. This would contribute to a decrease in ionization energy. So this is correct. For part 2, electrons are more delocalized as ionic radius decreases. That doesn't really apply here, because we're talking about our neutral atoms that we're taking off the first electrons from. So ionic radius doesn't apply to this whole discussion here, right? Each succeeding atom has one more quantum shell than the other. That's true. Remember I said as you go down, you're adding a shell? So this is true. And that's why it's easier to remove the outermost one, because each time you go down, you're adding one more shell. So that outermost electron shell is further away from the nucleus. So it's easier to take off that outermost electron, right? So our answers here would be 1 and 3. So that's B for 36, okay? All right, so moving down to 37. 37 says, group 4 elements show an increasing tendency towards metallic character as atomic number increases, right? So group 4 elements, let's just jot those down real quick. So the group 4 elements are carbon, silicon, germanium, and then we have tin, and then we have lead, right? These are the ones that we're concerned about for CAPE. So they're saying now as the atomic number increases, which would be as you're going down the group, you become more metallic, is what they're saying. More metallic character, right? More metallic as you go down the group. Why might that be the case? What might account for that as the atomic number increases? Well, as you go down the group, remember we said that, let's look at the first one. The +2 state becomes more stable than the +4 state. So the +4 state is going to be our dioxides. So that would be, we have in the +2 state, we have CO, we have SiO, we have GeO, and then SNO and PbO. Right? Remember now, if we drag back your memories to the characteristics of these oxides, as you go down the group, the lead in the 2+ state becomes more stable, right? And so this is in fact more stable. So the +2 state becomes more stable than the +4 state. So these are the +2 states over here, and then the +4 states would be carbon dioxide, silicon dioxide, germanium dioxide. Then we have SNO2 and we have PbO2, right? Now remember, in these are the +4 states. In the +4 states, the stability, right, increases this way, and in the +2 states, the stability increases this way. So the arrow means increase in stability, right? And so if your +2 state is more stable, that means that you have a metal that can participate in an ionic bond with a non-metal or like oxygen. And so that's what we see here, is that Pb really likes being in this state and being a metal that way, okay? So the +2 states become more stable than the +4 state. As you go down the group, the +4 state become more stable than the +2 state. That's not true. As you go down the group, right? As you go down the group, the +2 state is more stable, right? As you go up the group, the +4 is more stable. So that's not true as you go down the group. So this is not true. The valence electrons in the +4 state do not partake in bonding. That's not true, because they do partake in bonding, but these are more what? Covalent bonding, right? And not ionic. So the +2 state, where we have like these monoxides, is where we're gonna have the metallic nature of these elements increasing as you go down. So now you're able to have ionic bonding over here, and that's because of the metallic nature of the lead in this +2 state, where it's more stable, right? So 37 is gonna be A, right? It's because the +2 state is more stable than the +4 state, where we can have that metallic character being increased, okay? All right. So moving along now to 38. 38, 38 says, which of the following oxides of elements in group 4 is the least acidic in character? Okay, least acidic. So in terms of acidity, the non-metal oxides are the most acidic, right? Most acidic. So let's just remember that at all times, that non-metallic oxides are going to be mostly acidic, the most acidic of the group. And then the metal oxides are more basic oxides, right? So metal oxides are more basic oxides. That's their character. They're basic in nature, right? And so what happens now? Let's look at this. Tin is metallic, but not as metallic as PbO2. Because remember, we said that as we go down, we increase in our metallic nature, right? As we go down. And so this is a +2 state. So we're in a +2 state. So the Pb is going to be super metallic in character. And as we said, metallic oxides are basic. So this one is going to be basic, which means it's the least acidic, okay? So 38 is going to be B. This is going to be super acidic. This is going to be super acidic because they're oxides of nonmetals. And then this is in the +4 state, and it's also not as metallic. This tin is not as metallic as the lead. And so this one is also going to be super acidic. So the least acidic will be this one here, which is when the lead is more metallic in nature, most metallic in nature in this +2 state, right? So it's going to be basic, right? And not acidic at all. So 38 is going to be B. All right. So moving along to 39. 39 says the decrease in volatility going down group 7 cannot be described by which of the following. So let's write out our group 7 elements real quick. So we're going down the group. We have our F2. We have Cl2, and these are gases, right? Then we're going to have bromine here, which exists as a liquid. And then we're going to have our iodine, finally, which exists as a solid. No, when we talk about volatility, we're talking about the ease of that particular element to go into a vapor phase. So how easy it is to vaporize that. These are already vapors, so it's going to be easy. They're already vapors, but as we go down, we go from gas to liquid to solid. It's going to be harder to make a solid go into the gas phase. So there's a decrease in volatility as we go down the group. Why might that be? Is the decrease in volatility because of the strength of the van der Waals force is increasing? That's true. Is it because electropositivity increases? That's not true. That's not true. The electropositivity has nothing to do with volatility. Volatility is a physical property, right? Physical property, right? It has to do with the structure and bonding, right? And so the structure and bonding, the strength of the van der Waals forces would be the reason why. The size of the atom increase, that would be a reason why it's harder to break those up to make it become a liquid. And in fact, it's a solid. That's how it exists naturally. The molecular mass also increases. So these would be reasons why the volatility increase. This wouldn't be able to describe it. We can't use a chemical property to describe a physical phenomenon or physical property of volatility. We can only use these structure, right? These structural things, these structural descriptions, and these are all true. These are all valid reasons why we see a decrease in volatility, right? And so the electropositivity thing is the one that we cannot use to describe it, okay? So 39 is B. And so we're moving along to 40. 40 says that a student tests an unknown sample with a few centimeter cube of, so this is silver nitrate, aqueous silver nitrate, followed by a few centimeter cube of dilute ammonia, aqueous ammonia. Which of the following observations would confirm that the sample contains a bromide ion, right? So remember now, when we have a bromide ion and we add silver nitrate to it, we're going to first and foremost, we're going to form AgBr. That's a solid precipitate, and that's going to be a creamish / off-white precipitate, right? So cream or off-white is the color of that precipitate that's gonna get formed first and foremost, right? So that's what we're gonna see first. So in the precipitate with AgNO, it's not gonna be white, it's not gonna be white, it's gonna be one of these. So the answer is gonna be between these two, right? No, when we so both of these are correct for the precipitate with AgNO3. Now, when we dissolve in dilute, when we use dilute ammonia, right, the AgBr is only sparingly soluble in that. It's not readily soluble, it's only sparingly soluble. So we'd see that it's we get rid of a little bit of the precipitate, but for the most part, it's still there, right? So it's sparingly soluble in this case, and so we can rule out this part, this D option here. It's not gonna be readily soluble. What it would be readily soluble in if we had concentrated ammonia, but that's not what we have. We have dilute ammonia, so the silver bromide will only be sparingly soluble, and so that's what we'll see, and that would confirm the presence of a bromide ion, okay? So again, the bromide ion, if we add AgNO3 to an unknown sample and we see an off-white precipitate, we can say, oh, that could be bromide. The bromide ion is present in there. And if we add dilute NH3 and we see that it's only sparingly soluble, then we can say, okay, for sure, that's the bromide ion, okay? So our answer for 40 is gonna be C. Okay, so moving right along to 41 now. 41 says that transition metal complexes contain a central metal atom or an ion that's surrounded by ligands, right? So for example, say I have my manganese 2+, and I have that being surrounded by these ligands, right? So my ligands are going to be giving it electrons to form like a dative covalent bond, right? So that's how transition metal complexes work. Then we're saying which of the following does not explain why the complexes are formed. So what is the key thing towards complex formations, right? Why do these transition metal form complexes, or these transition metal ions form complexes? It is, in fact, due to the presence of lone pairs on the ligand. So this is correct. This can explain why complexes are formed. It is, in fact, due to the presence of vacant d orbitals on the metal atom or ion, right? So that can explain why complexes are formed. The formation of covalent bonds between the metal and the ligands, that is true. As we said, there's a dative covalent bond that gets formed when that ligand donates its electron to the metal ion, right? What's not true, and they ask us what's not true, is this one. The complex ion formed is stable with respect to its constituents. That's not necessarily true. That's not why complex ions are formed. It's not really a stability argument per se, right? Stability arguments really only come into play when you're doing ligand exchange, not for complexing in the first place, not for complexation period. Complexation is because you have lone pairs on the ligands, you have a vacant d orbital that you can push those ligands in, those lone pairs into, and you have covalent bonds that form, and that's how we get complexes, right? It's not because the complex ion formed is stable with respect to its constituents, okay? So D is the answer here. This is not true, and they're asking us what does not explain it. That's D, okay? So 42 now says, which of the following represents the electronic configuration of the Mn3+ ion? Right, so let's write that one out. So the Mn3+ ion now, let us write the electronic configuration of that. Let's write that one real quick so we see what that is. Well, let's write what Mn is, right, before we've lost those 3 electrons. So when we write out Mn, let me write that out for you real quick here. Mn, let me write Mn on the screen for you. So the Mn would be this, right? So Mn, so the Mn, before we take off anything, is gonna be AR. It's gonna be our AR, and then 3D 5, right? And 4s2. So that's just the Mn neutral atom, 4s2, right? So if I take off 3 and I end up with my Mn 3 plus, it's gonna end up being Ar. And then I'm gonna take off these 2 and then 1 from here. So it would be 3D. So take off 2 here and 1 from here. So it'd be 3D4. Okay. So let's see what matches that in terms of a picture here. So we have 4 in the d orbital. So that would be 1, 2, 3, 4. And then our s is empty. It's completely gone, right? So you see that 1, 2, 3, 4. That's 4 in the d. And then we have nothing in the s. Okay. So that's B. 42 is B. Right? So just remember now, we have our neutral Mn and we're taking off 3 electrons, losing 3 to become the Mn3 plus ion. So we're going to take off 2 from the 4s and then 1 from the 3D. And so we end up with 4 in our 3D and nothing in our 4s. So 4s is empty, 3D has 4, B is our answer for 42. Okay? So moving along now to 43. 43 says transition metals can exhibit more than one oxidation state because they have more than one free electron. And that's not true. It's not because they have more than one free electrons. Like that's not true, right? Do they can exhibit more than one oxidation state because they have different colors? No, that's not really why they would have more than one oxidation states. They have different colors because they have more than one oxidation state, but that's not why they have more than one oxidation states, right? What is the reasoning? Like the reason on a chemical level why they have different oxidation state. And that's because they have similar energy levels for the 3D and the 4s, right? Remember, we look up here and we just said, okay, if we're going to form our Mn3 plus, we're going to take from the S as well as the D. That's because they're similar in energy, where we can take from here and take from here, and then we take off another and then another. And so that's why we have multiple oxidation states, because the energy levels for the 3D and the 4s are fairly similar. And so that's the reason why. The incomplete d orbital stuff has to do with color formation, and that's not why they have more than one oxidation states, okay? The more than one oxidation state is because of the similarity in energy levels. That's where that comes from. So this is not correct either, and our answer is C, right? So 43 is C. So moving along to 44 now. 44, item 44 refers to the following information. An unknown salt sample, so that's FAL, is subjected to analysis and the results are shown in the table. So we have potassium iodide aqueous going to Fa, and this is our unknown thing here. And we see no visible reaction, right? And then when we add ammonia to this salt, we see a white precipitate that's insoluble in excess ammonia. So if we have a white precipitate that's insoluble in excess ammonia, that can really only be one cation, right? That can be, let's look among these options. So it can be deduced most likely that the cation in this salt is what? It's not going to be zinc. It's not going to be Zn2 plus, because Zn2 plus wouldn't be insoluble in excess ammonia. It would dissolve, right? It would just completely dissolve and we wouldn't have a precipitate anymore. So that's not Zn2 plus. Na plus, that's a sodium, that's a group 1 metal. It's not going to form a precipitate, period, right? And we know that if we have a precipitate and the lead ion is present, we would see a yellow precipitate and not a white precipitate. And so this is not our answer either. And so that leaves us with aluminum, right, as our possible cation that's present here. And the reason why is because aluminum is insoluble. The aluminum 3 plus ion is insoluble in excess ammonia, and it would give us a white precipitate. So A is our answer. Okay, so we were able to rule out all of these. And so we're left with 44 being A. All right. So 45 and final, when a silver nitrate solution followed by dilute ammonia is added to a solution containing chloride ions, which of the following is the formula of the complex formed, right? So say we have Ag, let me write the first step. We have AgNO3, and we're adding that to a chloride solution that has chloride in it. We're going to end up with this, right? So we're going to end up getting AgCl. That's what we're going to get as our products. And of course, we would have gotten the nitrate ion being displaced, right? So that's what we would have gotten. And then they're saying now we're adding dilute ammonia to this silver chloride precipitate. When we do that, what's gonna happen is that these ammonia are gonna come in and exchange for these chloride ligands, and we're gonna end up getting AgNH3, 2, and then everything has a positive charge. The whole complex has a positive charge on it, and then these chloride ligands are gonna get displaced, okay? And so they're asking us the formula of the complex formed after these successive reactions, and that's actually this complex that they're asking us about, and so that's C here, okay? So this is just a ligand exchange reaction for this final step. In the first step, we have the silver nitrate, adding it to the chloride, and the chloride is gonna go in here and form a silver chloride, right? And then that now is gonna react with this dilute ammonia. We're gonna get displacement of this chloride ligand, and we're gonna get the ammonia going in there and forming this complex, okay? So that's here, that's C, so 45 is C. And with that, we've come to the end of this past paper one session. I hope this was helpful for you. Definitely go ahead and give this video a like. Drop a comment down below. Let me know if this was helpful for you. Share the video with a friend. Subscribe to the channel, and I'll see you in the next video. All the best in your exam.